good morning. Today we are going to see the different conditions for vapor compression cycle refrigeration system. So in our first lecture we saw that how that vapor compression cycle refrigeration system work. So there is one compressor, whatever be the intake to the compressor, it will get compressed to very high pressure and high temperature. Vapor refrigerant, that high pressure, high temperature vapor refrigerant then pass through condenser unit where it get condensed, that means it convert into liquid form. That liquid is then passed through expansion device where pressure is reduced, and then low pressure, low temperature liquid refrigerant pass through evaporator unit where it extract the latent heat from food content and it become a mixture of vapor and liquid. So now we are today going to study what are those conditions under which vapor compression cycle refrigeration system will represent on pH, pressure versus enthalpy, and temperature versus entropy diagram. And along with this we will see how to calculate those entropy and enthalpies at particular condition. So first condition, so when VCC cycle, when the outcome of a compressor is a dry saturated vapors. So dry saturated vapors after compression. So first condition is dry saturated vapors after compression. So imagine after compression the condition of refrigerant is high pressure, high temperature, exact dry saturated. So whenever we are saying dry saturated, so on this graph, we know that there is one critical point, that is critical point. On right hand side of critical point, it is saturated vapor line. So this curve belongs to saturated vapor line. And on left hand side of this critical point, it is saturated liquid line. So this is saturated liquid line. And whatever be the content inside this dome, inside this curve, it is a wet condition. Wet condition means it is a mixture of liquid and vapor. So on this line, it is saturated liquid. After that, this liquid become a mixture of liquid and vapor. When it reach to this curve, then it become completely saturated vapor. After this, there will be a superheating, and before saturated liquid, there will be a subcooling. Same on this TL diagram also, this is a critical point. Right hand side of critical point is a saturated vapor curve. And left hand side is a saturated liquid curve. And in between this, it is a mixture of liquid and vapors. Now, the strength of a mixture, that's means how much dry vapors are there in a mixture of dry and wet refrigerant, it is denoted by dryness fraction. So if I am drawing a dryness fraction line, so suppose this is X value, suppose 80% dry, so 0.8 dryness fraction. This is X value, suppose 20% dry, so X value will be 0.2. This may be a 50% dry, so X value will be 0.5. So dryness fraction, because in a mixture of wet steam, that is a mixture of liquid and dry steam, we must identify how much steam is dry. On this graph, it is completely liquid. When we are shifting towards this side, So your liquid, some portion get converted into vapor. So we come to know 20% vapor, 80% liquid. Again, if we move ahead, so here at this point, we come to know 50% liquid, 50% vapor. Here 80% vapor, 20% liquid. When we reach to saturation vapor line, completely it is converted into vapor form. After saturation, no doubt, it will be a superheated. So likewise, in the dome, we can identify how much steam is or how much vapor is dry with the help of dryness fraction. Same way, there will be a dryness fraction line on pH diagram also. So this is saturated liquid. In between this, there is a different dryness fraction weight vapors. When it reaches to this curve, it will be completely saturated vapor. Now the first case, when dry saturated vapors after compression. So it means it is not dry saturated condition before compression. So whatever be the refrigerant entering into compressor, it is not a dry saturated. It enter in a wet condition, and after compression it become a dry saturated. So whatever be the curve point after compression will lie on this dry saturated vapor line, vapor curve. So we have to locate after compression point on this. So suppose this is point which is after compression. Compression process is assumed as adiabatic. So compression will be considered at constant entropy. So constant entropy curve on pH diagram. So constant entropy line on pH diagram is always a curvicle. But on TS diagram, it is exact vertical because the entropy is constant. So this is the point on dry saturated vapor. That means after compression, your vapor is exactly dry saturated. So before compression, it must be a wet. If it is a wet vapor, so it will lie in between this. So this is point 1. Where we are entering our refrigerant in a condition of wet as a mixture of a wet and vapor, that is liquid and vapor refrigerant. So wet condition is entered into the compressor, and adiabatically it is compressed. So adiabatical compression, so it will be a curvicle line, and after compression it will become exact dry saturation. So vapor become exact dry saturated. So this is point 2. So this curve represent adiabatic compression. So entry to the compression is wet vapor. When we compress it, its pressure increases. We can observe that on y-axis pressure is increases, temperature increases, its enthalpy increases. So during compression, we increase the pressure and temperature, and the vapor condition become, that refrigerant become dry saturated. After compression, we supply this high pressure, high temperature, dry saturated refrigerant into condenser. What happens in condenser? In condenser, it extract latent heat. So it converted into liquid form. So not instantly it converted into liquid form. Whatever be the dry saturated vapor is there after compression, when it is supplied to condenser, so as it is removing its latent heat, so it start converting into liquid. So some portion get converted into liquid, the remaining portion remain vapor. So it is come again in a mixture zone, that is wet vapor zone. Again, reducing vapor content, increasing liquid form. So likewise, ultimately it converts all vapors into saturated liquid. So this is the inlet point of condenser. At outlet we get exact saturated liquid. That means all vapors get converted into liquid form. This is condensation process. So this is point 3. So 2 is the entry point to the condenser and 3 is the exit point of the condenser, where we obtain high pressure because pressure is same. At the entry point, pressure is P2. At exit point, pressure is P3, and we observe that this is constant pressure process. So condensation is a constant pressure process. So 2 and 3 having the same pressure, but temperature is reduced. Sorry, temperature is same because phase change takes place at constant temperature. But as we are removing latent heat, so we observe that there is a reduction in enthalpy. So enthalpy at point 2 is different, higher, and when we removing latent heat, it gets changed into liquid form, so enthalpy 3 is lesser. So temperature is constant because we are expecting only latent heat, but enthalpy is reduces. So after condenser, we supply that high pressure, low temperature, liquid refrigerant into expansion device. Expansion device where throttling process happens. And we know that in throttling process, enthalpy always remains constant. So 3 point is the entry of expansion valve or throttle valve, and during throttling, enthalpy remains constant, so we get a constant enthalpy line except vertical because enthalpy is same. And at the end of throttling, so outlet of throttling, no doubt, it is low pressure. Pressure is high before throttling. During throttling, enthalpy remains constant, and that expansion device or throttling valve reduce the pressure. So pressure is reduced at the exit of that expansion valve. This is point 4. So now low pressure, low temperature refrigerant is passed through evaporator. Now in evaporator unit, it extracts the latent heat from food content. So as it is absorbing latent heat, so its enthalpy increases and its phase will changes. So here we observe that it is more wet vapor condition, but as it is absorbing latent heat and converting into vapor, so its wetness reduces. So if I observe, so dryness fraction at point 4 is lesser, dryness fraction at point 1 is more. So after evaporation, we observe our refrigerant become wet and it reach to condition 4. This is expansion process or throttling process, and this is evaporation process. So this is the cycle on pH diagram. Now we will see how it is represented on TS diagram. So here this is critical point on this side. This is a saturated vapor curve, and on left side this is saturated liquid curve, and in between it is a wet vapor. Wetness can be measured with the help of dryness fraction. Now, as we know that after compression, we reach to dry saturated curve. So that means in TS diagram also our point 2 will be lie on this dry saturated curve. This is point 2. So entry of the compression is a wet zone. That is point 1 is lie in this dome. So it will be a wet vapor, and after compression it becomes dry vapor. So compression process is adiabatic. That means entropy remain constant throughout the compression. So our compression process will be represented as vertical line. So our point 1 lie in wet region. This is our entry point of compressor, and it is adiabatically compressed and it reach to dry saturated vapor. Then after it enter to condenser, in condenser temperature remains same. We are just removing latent heat. So temperature remains same, but its phase gets changed continuously, and at the end of condenser, it becomes dry saturated liquid. So our point 3 lie on this dry saturated liquid. After this, we supply this refrigerant to expansion or throttling valve, where throttling process takes place, and throttling process, that is a constant enthalpy process, is a curvicle if I am drawing on TS diagram. So it is not a straight line because entropy, constant entropy is a adiabatic compression only. So when I am drawing constant enthalpy process on TS diagram, so it becomes a curvicle line. So this is point 4. This is expansion process. So dry saturated liquid is entered into the expansion or throttling valve, and during this, no doubt pressure will reduce, but it becomes little bit wet. And this wet refrigerant is then allowed to pass through evaporator, where it extracts latent heat. As it absorbs the latent heat, its entropy will increase. Entropy increase, so we observe the increase in entropy, as well as its dryness will improve. So dryness fraction 4 is lesser than dryness fraction 1. It means it becomes more dry steam. So this is evaporator. Now, if I like to calculate the enthalpy, so enthalpy of point 1, it is in wet zone, so it will be HF1. HF1 plus dryness fraction at point 1 into HFG1. So HFG belongs to this zone. HF means unsaturated liquid. So whatever be the condition 1. So one point having some particular temperature. So at T1 temperature, I will find out HF1 plus I will measure the dryness fraction at point 1, that is X1, multiply by HFG1. So it gives H1. Then for H2, enthalpy at point 2. So it is on dry saturated vapor line. So it is nothing but Hg2. This is at T1 temperature and this is at T2 temperature. H3, so enthalpy at this point, which is on saturated liquid line, so it will be HF3 and it will be calculated on T3 temperature. And H4, so remember H1 and H4 lie in wet vapor, so H4 will be HF4 plus X, that is dryness fraction at point 4 into HFG4, and this will be calculated on temperature T4. Similarly, if I am trying for entropy, so entropy at 1, so S1, so it will be SF1 plus X1 into SFG1. Simply we are replacing H by S. So formula remains same. No doubt it will be calculated on T1 temperature. S2, entropy at point 2, it is lie on dry saturated vapor. So S2 will be SG2, it will be calculated at T2 temperature. S3, dry saturated liquid line, so it will be SF3, calculated on T3 temperature. And S4 will be SF4 plus dryness fraction at 0.4 into entropy FG4, and this will be calculated at temperature T4. So this is the condition if after compression we observe our refrigerant become dry saturated vapor. So after compression we observe our refrigerant condition on this dry saturated curve. This is first condition. Now the second, suppose after compression we don't reach to dry saturation point. After compression we still in a dome, that means our after compression our refrigerant is again in a wet condition. So second type is wet vapors after compression. So what happens if even though we compress our refrigerant but the compression is not reached to dry saturated condition, it will lie in a wet zone. So how to represent our pH and TS diagram? So in this condition we know that on pH diagram after compression our point 2 is not on dry saturated point. Here also there will be a critical point. This will be saturated line, vapor line. This will saturated liquid line. So after compression we know that it is not reached to dry saturated vapor. So our after compression point is lie in this wet zone. This is point 2. No doubt before compression it will lie in the wet zone, but after compression its dryness is improved because it becomes little bit more dry. So our point 1 will be more wet condition, and this is adiabatic compression which is shown by curvical line. So this is a compression process, adiabatic compression. So entry point having more wet vapor condition, after compression it become higher dry condition, but it is not reached completely to saturated dry. Its dryness fraction improved. So dryness fraction at 1, dryness fraction at 2. So dryness fraction at 2 is more than 1. So it become more dry, but it is not reached to exact saturated, dry saturated vapor condition. So it lies in dome itself. After this, we supplied this into a condenser. So in condenser, its latent heat is removed, temperature remains same. There is no effect on pressure. So at pressure, high pressure, temperature remains same, low temperature, and phase gets changed to saturated liquid. So this is our condenser. So after condenser, we observe that our refrigerant becomes saturated liquid. Then after we supply this refrigerant into throttling device, where throttling process is constant enthalpy process. So exact vertical line. This is the expansion process, constant enthalpy line, and after this throttling process, we supplied refrigerant to evaporator unit where it absorbs latent heat, so its dryness fraction improves. So dryness fraction at 4 is less, and absorbing heat, its dryness fraction becomes more, and it reaches to 1 condition. So this is evaporation. And same cycle on TS diagram. So TS diagram also there is one critical point. On right hand side it is dry saturated vapor line, and on left hand side it is saturated liquid line. Now to represent this wet vapor after compression, so in TL diagram also our point 2 will be lie inside the dome. So it is wet steam, wet vapor. As compression is adiabatic means constant entropy. So before compression, point 2 will be on vertical line. So this is point 1. Adiabatic compression takes place, so entropy remains same, and it reaches to point 2. At point 2, it is supplied to condenser, so latent heat is removed, so temperature remains same, only phase change takes place. So whatever the dry steam is there, that is dryness fraction having x2, this is supplied to condenser and it becomes completely saturated liquid, and outlet of condenser is 0.3 saturated liquid line. This is condensation process. After condensation, there will be a expansion through a throttle wall or expansion wall, and that is a constant enthalpy process. But constant enthalpy process on TS diagram, it will be a curvical. So this is expansion process or throttling process, and it reaches to condition 4. This condition 4 refrigerant is passed through evaporator where latent heat is absorbed from food content and its dryness fraction is improved, and this is the evaporation. So when dry saturated vapor after compression, this pH and TS diagram representing. Wet vapor after compression, this pH and TS diagram is a representation. Now for calculation part, point 1, 2 and 4 lie in wet region, but it having different dryness fraction. If I am drawing a dryness fraction, so it having a dryness fraction 4 point, it having dryness fraction 1, dryness fraction 2. So dryness fraction are different. So if I am calculating H1, so it will be a wet vapor, so H1 will be HF1 plus dryness fraction at 1 into HFG1. If I am calculating H2, it is again in wet zone, so HF2. HF2, it is simply the notation. This is going to calculate at temperature T1. So 1, 1, 1. HF2, X2, dryness fraction at 0.2 into HFG2. This will be calculated at temperature T2. H3, so H3 is the actual saturated liquid, so it is simply HF3 and it will be calculated at T3. And last H4, again lying wet zone, so HF4 plus dryness fraction at 0.4 multiplied by HFG4, and this will be calculated at temperature T4. And the same manner for entropy, so S1, so SF1 plus dryness fraction X1 SFG1, S2 SF2 plus dryness fraction X2 SFG2, S3, so it will be SF3, and S4, so it will be again SF4 plus dryness fraction 4 into SFG4, and it should be measured at corresponding temperature. So S1 will be at T1, S2 at T2, S3 at T3, and S4 at T4 temperature. So these are the two conditions. Now after this, there are remaining three conditions are there. The remaining condition, when after compression your vapors become superheated, then how to represent on pH and Ts diagram. Next, imagine before compression we are supplying a dry saturated. So after compression, superheating. Before compression, if suppose your vapor are superheated condition, then and if there is a subcooling, here we are assuming after condenser it become a saturated liquid. But if it becomes subcooled, then how to represent? So there are almost 5 different conditions. So today we just saw that dryness saturated vapor after compression, wet vapor after. So remaining 3 types. So we will start. We know that how to draw pH and Ts diagram. When at the end of compression, the condition of refrigerant is dry saturated, and when it is a wet condition, that means after compression it is not reached to the dry saturation condition, it lies in a dome shape itself, that means it is a wet vapors. Now the next is when the vapor is superheated, that is third condition. At the end of compression. So imagine I am compressing the refrigerant, and after the compression I observe the vapor reach to the superheated condition. Now in that case, if the vapor reach to superheated condition, that means it is not lie on this dry saturated vapor curve. Even though it is not lie on this dry saturated vapor curve on TS diagram, it will be on this superheated zone. Suppose this is the superheated zone, this is point 2. If point 2 lie inside the dome, then it is wet zone. If it is lie on this curve, then it is dry saturated vapors. If it is lie beyond this curve, it is a superheated zone. So after compression, it reach to superheated condition. So point 2 lie here, and that means the compression process, the intake is, we are assuming it is dry saturated vapor. So this is our first point. So intake is dry saturated vapor. It may be case that intake is in wet steam, wet region, but after compression it reaches to superheated. That is also possible. But here we are assuming that the intake to compressor is dry saturated condition, and after compression it reach to superheated condition. So if your steam is at superheated condition, so when I supplied it to a condenser, so directly it is not going to convert into liquid form. Why? We have to reduce this degree of superheat and bring our vapors to dry saturated condition there. So suppose I am reducing the temperature, but pressure remains same, because in a condenser pressure does not change. So I am reducing the temperature of the superheated vapor. It brings back to saturation condition. Now my vapors refrigerant become dry saturated. So it is vapor condition but superheated. When I reduce the temperature, sensible heat is removed, so its temperature decreases. but pressure remains same at constant pressure. Temperature decreases and it reaches to dry saturated condition. This is 2 dash. And after dry saturated condition, if I further remove the heat, so that heat will be a latent heat, so phase change will be there. So this is point 3 and this is the condenser process. So from point 2 to 2 dash, it is reducing degree of superheat. So this is reducing degree of reduction in degree of superheat. So your superheated steam bring back to dry saturated condition first by extracting sensible heat, and then after we are extracting latent heat, so it get converted into liquid form, and at the end of condensation it reach to saturated liquid. Then after it is passed through throttling wall or expansion wall, so enthalpy remain constant. So this is expansion process, and it reach to point 4, and then from point 4 it is enter into evaporator where it extract latent heat from food content, its enthalpy is increases, and this is evaporation. So when there is superheated steam after compression, so first we have to bring that superheated steam, superheated vapors to dry saturated condition. Then after the phase change will start. That's the conversion from vapor to liquid will start. If I am plotting this on TS diagram, so my second point after compression will be in superheated region. And compression is adiabatic. So I will draw a straight vertical line because adiabatic process entropy remain unchanged, and we are considering intake to compressor is a dry saturated vapor. So this is my inlet to compressor point. So compressor, this is the condition when I enter this refrigerant into compressor. Adiabatically it is compressed, and outlet of compressor is 2, which is superheated. Then after I have to reduce the degree of superheat. When I reduce the degree of superheat, that means I am extracting sensible heat. If I remove the sensible heat, so definitely temperature will decrease. So point 2 is here. As I am removing sensible heat, so its temperature will decrease. So 2 point temperature is higher, and this is 2 dash. So first I decrease the degree of superheat. During this decreasing degree of superheat, I extract the sensible heat, so temperature is reduced. And then after when it reach to dry saturated vapor, then after I extracting latent heat, so phase change will there. So it will convert it into liquid form, and after condensation it reach to saturated liquid point 3. After condenser we supplied it to expansion wall, so constant enthalpy process will be appear curvical on TS diagram. So this is the expansion process, point 4, and from this point 4 we enter this refrigerant to evaporator unit where it extract latent heat and entropy will increase. So this will be the process on TS diagram if the outlet of compressor is a superheated condition. Now here if I am finding enthalpies, so enthalpy H1, this point. So enthalpy H1 will be the enthalpy of this vapor at dry saturated condition. So it will be Hg1 and it will be measured at temperature T1. H2, it is superheated, enthalpy of superheated steam. How to calculate this? So enthalpy of superheated steam is Hg2 plus, now due to superheat, Cpg. But this Cpg is at T2 dash. Cpg multiplied by T2 minus T2 dash. Always remember higher minus lower. So enthalpy at superheated condition 2 will be Hg2 plus Cpg, specific heat of vapor, but at which temperature? T2 dash. So we are taking Cp on this curve line at a temperature of T2 dash, multiply by T2 minus T1. T2 minus T2 dash. H2 dash. Now suppose I am interested to calculate the H2 dash. So H2 dash is nothing but the enthalpy of vapor on saturated, dry saturated curve. So it is nothing but Hg2 dash, and it will be calculated on T2 dash. Now H3 is HF3, and it will be calculated at T3 dash. H4, so it is wet condition, so HF4 plus dryness fraction at 0.4 multiplied by HFG4, and it will be calculated at temperature T4. If I am talking about the entropy, so S1 will be Sg1 at temperature T1. S2, remember there is a change in the formula of H2 and S2. Sg2 plus Cp of gas, definitely at T2 dash, multiplied by ln of T2 upon T2 dash. This is the difference. If we are going to calculate the entropy and enthalpy of superheated condition, so in enthalpy we have to take a Cp multiplied by T2 minus T2 dash, but entropy we have to consider Cp multiplied by ln of T2 upon T2 dash. This is the only difference when we are talking about superheated state. Now the S2 dash is the entropy of dry saturated vapor at temperature T2. So it is simply Sg2 dash, and it will be calculated at temperature T2 dash. Next, S3. So S3 will be SF3. It will be calculated at T3, and the last S4. So similarly, S4 will be SF4 plus dryness fraction at 0.4 SFG4, and it will be calculated at temperature T4. So corresponding temperature, we will find all the values, put in the respective formula, and we are able to calculate the enthalpy of each and every point and entropy of each and every point. So this is when we obtain a superheated condition at the end of compression. The next is, imagine here the entry is at saturated, but imagine if the entry is itself a superheated condition. So no doubt entry is superheated, so definitely exit will be the superheated. Here exit is superheated, but entry is dry saturated. Now the next condition is, that is for superheated vapor at entry to compressor. So before compression, or you can say it is not an entry to compression, it is before compression. So most appropriate word is before compression. So before starting compression, if your vapor is superheated condition, then how to plot? So imagine this is the condition, first point, which is in superheated zone. So superheated vapor enter into compressor, then after compression, adiabatic compression will take place and it will reach its degree of superheat, and this is the exit of compression operation. So compression will end there. This is the compression process. So before compression already vapors are in superheated condition. After compression definitely reach to superheated condition. Then we will supply this to condenser, where first we remove out its sensible heat, so its degree of superheat will reduce and your vapor reach to dry saturated condition. This is 2 dash. So superheated steam, we extract a sensible heat, its temperature will reduce but pressure remains same. Constant pressure process. So temperature is reducing and we are bringing vapors from superheated condition to dry saturated condition. Then after we are removing latent heat, so its phase gets changes. First it becomes wet vapor and last it becomes saturated liquid at 0.3. So this is condensation. So this is the portion where we reduce the degree of superheat. Then after condenser, we supply this refrigerant to expansion device where throttling process takes place. So this is the expansion process where enthalpy, in expansion device, the enthalpy remains constant. So throttling process, enthalpy remain constant, so we observe a vertical line. This is expansion and it will reach to 0.4. So after expansion, we observe our vapors become wet and this wet vapor enter into the evaporator. When it enter into the evaporator, it extracts a latent heat from food content and its degree, dryness fraction will improve, so it become more dry, and once it reach to saturated dry condition. Now the question is, we can have a refrigerant at saturated dry condition, but how it becomes superheat before its compression started? So imagine our compressor is running at very high speed, its overall parts and all get heated. The refrigerant at this dry saturated condition when enter into the compressor during its suction stroke, so the body is already heated at high temperature. So when this vapor enter inside the compressor during suction stroke, so it absorbs the heat from surrounding all walls and that pump body, compressor body, and it becomes superheat. Before the actual compression start, during suction itself, when suction started, your vapor enter into the compressor, but surrounding wall temperature is high, so due to that wall temperature it gain heat and become superheated before the compression started. And when compression started, so compression will start compressing superheated vapor. So this degree of superheated will be because of the heated part, not because of it gets superheated due to extraction of latent heat. Why? Because refrigerant only able to extract the latent heat, not the sensible heat. So, because why it is not extract the sensible heat? Because that liquid refrigerant converted into vapor, and vapor don't have that much capacity to extract the heat. So, in refrigeration system, we observe that the latent heat is there. So, this compressor parts heat up it and bring it to superheated conditions. So, this is suppose 1 dash, and this is evaporation. Now, same process if I am going to explain on TS diagram. So, remember the first point is already in superheated condition. This is my first point. Before compression started. Compression process is adiabatic. So, I observe the vertical line, straight vertical line. This is compression A. Entry to compressor already superheated, compression end. Now I have to reduce the degree of superheat by extracting sensible heat. So I reduce superheated vapor to dry saturated vapor at point 2 dash. So during this reduction of degree of superheat, I am extracting sensible heat. So temperature will reduce from T2 to T2 dash. Then after I am extracting latent heat, so there is no change in temperature. Only phase change takes place. And due to this, after condensation, I observe the point 3. This is condensation. So this is the degree of superheat which is reduced. After condensation, I am supplying this refrigerant to expansion valve where throttling process takes place. So this is point 4. And after this point 4, I am supplying this refrigerant to evaporated heat where it extracts latent heat and it becomes more dry. Saturation temperature and enter into a compressor. So compressor surrounding temperature will superheat this vapor and it reach to 1. That's when this is our 1 dash. So so here increase in superheat, it is decreasing. Superheated vapor before compression. So compression start from 1, but already this 1 point lie in superheated zone. So before compression, our vapors are in superheated condition. Now in this case, how to calculate enthalpy and entropy? So H1 already in superheated condition. So how to calculate H1? So H1 will be Hg1 dash. Sorry, this one. Hg1 plus Cpg at temperature T1 dash multiplied by T1 minus T1 dash. So enthalpy at Hg1 plus Cpg, where we are calculating specific heat of this vapor at this point, dry saturated curve. So take a temperature T1 dash, that time calculate what is the Cp, and then T1 minus T1 dash. H2 is again superheated, so similarly Hg2 plus Cpg at T2 dash, remember not at T2, it is at T2 dash on the curve, multiply by degree of superheating temperature, that is T2 minus T2 dash. What is the temperature enthalpy at 2 dash? So H2 dash will be the nothing but Hg2 dash, and it will be calculated at T2 dash. H3, so H3 will be HF3 at temperature T3. H4, so in the same manner, HF4 plus dryness fraction at 0.4 multiplied by HFG4, and the last point 1 dash, so H1 dash will be, it is on dry saturated steam, so it is Hg1 dash, and it will be calculated at temperature T1 dash. Similarly for entropy, S1, so S1 will be Hg1 plus Cp of gas at temperature T1 dash ln of T1 upon T1 dash. Remember, this is the difference when enthalpy and entropy is calculated. For S2, Sg2 plus Cpg at T2 dash multiplied by ln of T2 upon T2 dash. Next, S2 dash. So entropy on saturated vapor line. So it is nothing but Sg at 2 dash, and it will be calculated at T2 temperature. Then S3. So SF3 calculated at T3 temperature. S4. So SF4 plus dryness fraction at 4 multiplied by entropy of fluid and gas at 4. And the last point 1 dash. So entropy at 1 dash will be Sg1 dash, and it will be calculated at temperature T1 dash. So these are the remaining two conditions. When first is after compression superheating, second is before compression itself it is superheated, and the last condition, if there is a subcooling. We know what is superheating. If point lie after this dry saturation curve, it is called superheating. If your point lie below or behind this saturation liquid, then it is called subcooling. That is the last portion. So let us see that last point, when there is a subcooling. In superheating, we added Cp ln of ratio of temperature, and for enthalpy we added Cp and temperature rise, that is T2 minus T2 dash or T1 minus T1 dash. Now we will see what happens when we are talking about subcooling. So this is a curve, saturated liquid curve, this is critical point, saturated vapor curve, this is critical point, saturated liquid curve, and this side saturated vapor curve. Now imagine there is a subcooling. Now how it is going to behave when there is a subcooling? So imagine We have a dry saturated entry point to compressor. This is point 1. After compression, it becomes superheated. This is point 2. This is a compression process. These superheated vapors are passed through a condenser where we first reduce degree of superheat and bring it to 2' condition. Then after we remove out latent heat, so it will bring to saturated liquid point at 3'. So it will be saturated liquid. Imagine if this condition is again reduced, then this is called subcooling. This is the point 3. So this is condensation. This is reduction in superheating, and this is subcooling. So this portion is known as subcooling. It also called as undercooling. So we are cooled down our refrigerant below the saturation condition. But the process is at constant pressure. Pressure is not affecting. Pressure is not increase or either decrease. So after that condensation, we supply this refrigerant to expansion valve where constant enthalpy pressure reduction process takes place. So this is constant enthalpy pressure reduction. So expansion process is there. So enthalpy remains same. And this condition, refrigerant enter into evaporator where it extract latent heat and reach to dry saturated vapors. This is evaporation. So this is subcooling, degree of subcool. This is degree of superheating. If I am going to draw this on TS diagram, so my first point lie on dry saturated curve. This is 1. When it gets compressed adiabatically, so I observe a straight line, entropy remains same. So this is point 2. This is a compression process. When I supply this high temperature superheated vapor to condenser, first it reduces its degree of superheat by extracting sensible heat. Whenever we extract the sensible heat, temperature will decrease. So it will reduce the degree of superheat. So temperature at point 2 is higher, temperature at point 2' is lower. That means we are actually extracting sensible heat. So temperature is reduced. So degree of superheat is reduced. Then after we extract a latent heat, so its phase gets changed and it converted into saturated liquid at 3'. At 3', we have a temperature equal to 2'. But we are not stopped here. We are again cool down it. That means subcooling takes place. When subcooling takes place, so its temperature again reduced. Condition is saturated liquid itself, but its temperature is reduced and it reached to 3. So this is 3' to 3 is a subcooling. Then after we allow this to enter into expansion valve, so this will be an expansion process, and it reached to point 4, and then after in evaporator it extracts a latent heat and become a dry saturated vapor. So when there is a subcooling, so we obtain such kind of graph. Superheated steam reduce the degree of superheat, reach to 2' temperature. Then after extracting latent heat, so temperature remains same and it become completely saturated liquid. Then after we remove a heat, so its temperature is reduced and it reach to subcool temperature, that is 3. And then after it enter to expansion and after expansion enter to evaporation. So this will be the representation of pH and TS diagram for subcooling. So when undercooling, this is fifth point, undercooling or subcooling is there. Undercooling or subcooling of refrigerant. Now in this case, how to calculate the enthalpy? So enthalpy at first H1, it is lie on dry saturated vapor line, so it is Hg1 at temperature T1. H2, so it is superheated, so it will be Hg2 plus Cp of gas or vapor at temperature T2 dash multiplied by T2 minus T2 dash. H2 dash, it will be Hg2 dash. It will be at temperature T2 dash because it is itself a dry saturated condition. Then H3 dash, it is saturated liquid point, so it will be HF3 dash calculated at T3 dash. H3 enthalpy at this point. Now here is the difference. H3 will be HF3 dash minus Cp into T3 higher temperature T3 dash minus T3. Here we have to remove this amount, then it becomes subcooled. So enthalpy of subcooled refrigerant condition will be HF3 dash at this point, whatever be the enthalpy, minus Cp into T3 minus T3. Then H4. So regularly HF4 plus dryness fraction 4, HFG4. So this will be the enthalpy calculation if there is a subcooling. Now entropy calculation. So in entropy calculation, S1, it will be Sg1 at temperature T1. S2, it is Sg2 plus Cpg at T2 dash ln of T2 upon T2 dash. S2 dash will be Sg2 dash at temperature T2 dash. S3 dash will be SF3 dash at temperature T3 dash. S3 subcool point. Now here S3 and S3 dash both lie on dry saturated curve line. It is not the same case. It is not lie on saturated liquid line. Only 3 dash lie on saturated liquid line. So when we are calculating enthalpy at point 3, so we have to subtract Cp multiplied by T3 dash minus T3. But here, when we are calculating entropy 3 dash, so it will be SF3 dash at temperature T3 dash. And when entropy at 3, so it is SF3 at temperature T3. Because both points lie on saturated liquid line. S4. So SF4 plus dryness fraction 4, SLG4. This will be the formula. So this is the total 5 conditions to plot pH and TS diagram for vapor compression cycle refrigeration systems.